Our solar system began its journey roughly 4.6 billion years ago from a cold, dark molecular cloud of gas and dust. These clouds, primarily hydrogen and helium, are the birthplaces of stars and planetary systems. Imagine a swirling nebula, a chaotic yet beautiful dance of particles, the very ingredients of our solar system's genesis. Within this cloud, a region of higher density began to collapse under its own gravity, possibly triggered by a nearby supernova. As the cloud contracted, it spun faster, flattening into a rotating disk, setting the stage for the birth of our sun and its orbiting planets. The core, destined to become our sun, continued to accumulate mass, drawing in more material from the surrounding disk. As the core grew denser and hotter, the temperature at its center began to rise dramatically. This process of gravitational collapse and heating continued for millions of years, transforming a cold, dark cloud into a vibrant, energetic protostar. The protostar, a precursor to our sun, continued to evolve, its internal temperature and pressure steadily increasing, paving the way for the ignition of nuclear fusion. The nebular hypothesis provides a comprehensive framework for understanding the formation of our solar system. Developed over centuries, it posits that our solar system originated from a rotating cloud of gas and dust, known as the solar nebula. Early thinkers like Swedenborg, Kant, and Pierre-Simon Laplace recognized the flattened, disk-like structure of our solar system. The discovery of protoplanetary disks around other young stars has provided strong observational evidence in support of the nebular hypothesis. The hypothesis explains the overall structure of our solar system and the observed distribution of planets. The inner rocky planets formed closer to the sun, where temperatures were high enough to vaporize lighter elements, leaving behind heavier materials like rock and metal. The outer gas giant planets formed further out, where temperatures were low enough for lighter elements to condense into icy solids. As the protostar continued to accrete mass and contract, its core temperature reached about 10 million degrees Celsius. At this temperature, nuclear fusion ignited, marking the birth of our sun. Hydrogen atoms began to fuse together, forming helium and releasing enormous amounts of energy. The newly born sun, now a powerful source of energy, began to exert a profound influence on the surrounding protoplanetary disk. The intense radiation and stellar wind from the sun began to clear out the remaining gas and dust, shaping the environment in which the planets would form. The sun's gravitational pull held the planets in their orbits, preventing them from drifting away into space. The birth of the sun transformed a cold, dark nebula into a dynamic and energetic system, paving the way for the formation of planets and the eventual emergence of life. Surrounding the young sun was a swirling disk of gas and dust known as the protoplanetary disk. This disk, leftover material from the original molecular cloud, served as the birthplace of the planets. Within the protoplanetary disk, a process known as accretion began to take place. Microscopic dust grains collided and stuck together, forming larger pebbles. These pebbles grew into larger rocks and eventually planetesimals, kilometer-sized objects considered the building blocks of planets. The temperature gradient within the protoplanetary disk played a crucial role in determining the composition of the planets. Closer to the sun, only heavier elements like rock and metal could condense into solids. Further out, lighter elements like hydrogen, helium, and water could condense into icy solids. This gradient explains the distribution of planets. Inner rocky planets formed close to the sun, while outer gas giants formed further out. The formation of planets was a gradual process, taking millions of years. Planetesimals continued to collide and merge, growing into larger objects. These collisions were often violent, shattering planetesimals into smaller pieces or ejecting them from the solar system. In the inner solar system, where temperatures were high, planetesimals were primarily composed of rock and metal. These planetesimals collided and merged, eventually forming the four inner rocky planets: Mercury, Venus, Earth, and Mars. In the outer solar system, where temperatures were low, icy planetesimals were abundant. These icy planetesimals, along with rock and metal, formed the cores of the giant planets: Jupiter, Saturn, Uranus, and Neptune. These cores then attracted vast amounts of hydrogen and helium gas, forming the massive atmospheres we see today. The size and composition of a planet depended on its location within the protoplanetary disk and the availability of building materials. The giant planets Jupiter, Saturn, Uranus, and Neptune are the dominant players in the outer solar system. These massive planets, composed primarily of hydrogen and helium, are vastly different from the inner rocky planets. Their immense gravity played a crucial role in shaping the architecture of the solar system. Jupiter, the largest planet, is more massive than all the other planets combined. Its powerful gravity helped to clear out the remaining planetesimals, preventing the formation of a planet between Mars and Jupiter. This region is now occupied by the asteroid belt, a collection of rocky remnants from the early solar system. Saturn, the second largest planet, is famous for its magnificent ring system, composed of countless icy particles. Uranus and Neptune, the ice giants, are smaller and less massive than Jupiter and Saturn, composed primarily of water, methane and ammonia ices. Their bluish appearance is due to the presence of methane in their atmospheres. The planets did not necessarily form in their current orbits. Planetary migration, the movement of planets from their initial formation locations, played a significant role in shaping the architecture of our solar system. The NICE model proposes that the giant planets initially formed closer together than they are today. Gravitational interactions between the giant planets and the remaining planetesimals caused the orbits of the giant planets to shift, leading to a period of instability and planetary migration. This period of instability is thought to have caused a bombardment of comets and asteroids onto the inner planets, known as the Late Heavy Bombardment. This bombardment may have delivered water and other volatile compounds to Earth, playing a crucial role in the development of life. The migration of the giant planets also played a role in shaping the Kuiper Belt, a region beyond Neptune containing icy bodies left over from the early solar system. The Kuiper Belt is home to Pluto and other dwarf planets, as well as countless comets. The solar system, as we know it, will not last forever. In about 5 billion years, the Sun will exhaust its supply of hydrogen fuel and begin to evolve into a red giant star. As the Sun expands, it will engulf Mercury, Venus, and possibly even Earth. The outer planets will also be affected by the Sun's evolution. Their orbits will expand as the Sun loses mass, and they may even be ejected from the solar system altogether. Eventually, the Sun will shed its outer layers, leaving behind a dense, compact core known as a white dwarf. This white dwarf will slowly cool and fade over trillions of years, marking the end of our solar system's life cycle. While our solar system may eventually meet its demise, the elements forged in the heart of the Sun will be recycled into new stars and planetary systems, continuing the cycle of cosmic creation.